Good to see everybody. It's been a little bit. Like Professor Leishman was saying, this week we're going to be talking about storage allocation schemes, which includes a bunch of ideas and data structures directly relevant to your next project, which we're also about to launch. But before we get started, I wanted to let you know about the results of the quiz. So the staff has finished grading everything, and I don't think we've released it, but should have it back to you very shortly. But for now, this is a snapshot of the grade distribution. And the high order bit is just that you all did really, really well. So congratulations. I think the score distribution here is significantly higher than usual for the class. And in general, people all did quite well. But we'll have more to share when we release stuff very soon. And thanks to the staff for working really hard to get this graded very fast. All right, so with that, this week we're going to be doing a deep dive into storage allocation. So different schemes and data structures for allocating and freeing memory. And storage allocation systems can be a big factor in the performance of programs and systems in general. And so today we're going to be talking about some of the basics of allocators in general. And then on Thursday, we'll kind of level up and talk about issues and schemes for fast storage allocation in a parallel context where resource allocation becomes significantly more complicated because of the need to coordinate among concurrent threads. All right, so today we're going to address or talk about three major classes of storage management. And you've probably heard about all of these in one context or another, but we'll be digging into a bit more about how they work under the covers and thinking about, so you can think about their performance implications. So first we have stack allocation. And stacks are great because they're both simple and fast, but they have a fundamental limitation, which is that you can only allocate and free from one end. So this is how languages like C, lots of other languages you've probably used, generally manage local variables defined within your functions. Then at the more general end of the spectrum, we have heaps, which are, like I said, more general than stacks and allow objects to be allocated and freed in any order. So this is what you get from malloc and free or new and delete in C and C++ respectively. And finally, we'll touch a bit on different schemes for garbage collection, which is a rich family of techniques for automatically reclaiming heap memory so that you can malloc without having to worry about when and where you can safely call free. The system can handle that for you. All right, so let's start with stack allocation since it's the simplest. So stacks have only two operations, push and pop. And with stack allocation, push allocates a new object and pop frees the most recently allocated object. So a physical metaphor here is a cafeteria plate dispenser, although most of you are probably not using cafeterias this year. So you can stack new plates, push new plates in from the top, or take plates off the top. So we say allocating and freeing memory in this way is following what we call a stack discipline. Meaning objects are allocated and freed in a last in, first out order. So the object that was most recently allocated is also the next one that we're going to free. So you're already familiar with stacks, even if you don't think about them very much, because they're how languages like C manage all of the local variables and arguments in functions. So in C, the compiler uses a stack to store local variables and function arguments whenever you call or instantiate a function. When you do that, a frame or a set of stack variables is pushed onto the stack when a function is called. And then when that function returns, the corresponding frame gets popped. So stacks are nice because they're simple, fast, and easy to automate. One reason you don't think about them very much is that the C compiler automates stack memory management for you, so you don't have to explicitly do anything to allocate or free stack variables in your C code. The compiler takes care of all that. But importantly, you're also constrained to this specific structure or order of allocation and deallocation. But obviously, sometimes you also need to be able to keep around objects that you just allocated and free things that you allocated farther in the past. And you can't do that with the stack. So with the C call stack, for example, you can't even hold on to local variables past the lifetime of the function that created them. And that's why we generally also have to work with a memory heap. So heap allocation is a more general scheme where you can allocate and free objects in any order. So in C, you do this with the malloc and free functions that you're all familiar with, or in C++ with the new and delete keywords, which are basically different syntax for the same thing. So explicit memory management like this is one of the reasons why C and C++ are really efficient, but it's also one of the reasons why they're hard to use and prone to a wider class of errors than many higher level languages. So in these languages, working with a heap directly, the heap storage has to be freed explicitly. Any objects that you're done using, you need to explicitly call free or delete on. If you don't do that, you get a memory leak. So your program you wind up using an ever expanding amount of memory. And when you're doing this memory management explicitly, there's a whole class of bugs that you can create if you accidentally make mistakes. So for example, if you create dangling pointers, which are pointers to free or unallocated memory, you need to be careful that you don't dereference them after you freed them. And similarly, you need to be careful that you don't double free things, so freeing memory that's already been freed. And as you've started to see in this class, I think there's a whole class of tools that are really useful when writing low-level explicit memory management code in languages like C and C++. You have things like address sanitizer, which uses compiler-based instrumentation, or similarly Valgrind, that uses instrumentation and tracing to help find bugs like dangling pointers and double freeing. So those are really important to use if you want to have bug-free and safe and secure C and C++. It's important also to realize that many of the security bugs that you see in the world have to do with errors in memory management at this level of abstraction. And one final comment, in spite of the overlap in name, heap memory management or heap allocation doesn't necessarily have anything to do with heap data structures that you might have seen in the algorithms or data structures class, which are an efficient way of managing things like priority queues. All right, so heap allocation is essential to being able to write general programs and work with long-lived dynamic data structures, but it can be painful and difficult to have to explicitly free memory. So for short-lived programs, many of you have probably written code where you just leak and don't care because the memory will be cleaned up when your process exits. But in general, that's obviously bad. So we need some way to free and reclaim unused memory. So it would be nice if we could do that automatically rather than manually. Have the system or compiler or language runtime take care of it for us. And that's what garbage collection is all about. So unlike in explicitly managed heap storage, garbage collected storage doesn't require explicit freeing, which improves programmer productivity. This usually or often comes at the cost of some performance trade-offs, or at least some lack of control of the performance characteristics of your program. But like we talked about dating back to lecture 1, performance isn't something you can eat by itself. It's a currency that's useful to trade for other things, and often trading performance for safety and productivity by using things like garbage collection can be a really practical trade-off. So garbage collection is really common in higher level languages than C and C++. So you've probably used a bunch of garbage collected languages already, things like Python, Java, Julia, or any functional programming language like OCaml or Haskell, JavaScript, et cetera. All of these things are garbage collected. And it's one of the keys to the kind of higher level of abstraction, fewer memory bugs, and higher productivity of writing in those languages. But it's also part of the reason why they tend to be a little bit less efficient than C. So the basic idea of a garbage collector is that we're going to have some automated process that looks through what the current state of storage and figures out storage that the program can no longer access, and then frees or reclaims that. And we can do this in multiple different ways. So some of them maybe require pausing the executing program to look at what the current state of its memory is and figure out what can be freed. Other garbage collectors run in real time, modifying the allocation routine to look for opportunities to free incrementally as you move along. Or fancier garbage collectors may use concurrent data structures so that they can operate in parallel with the main program. Again, garbage collection usually comes at some performance penalty relative to explicit malloc and free. And it turns out that some of the reason for that is the fact that we have to have code that explicitly goes through and scans the contents of memory. But another relatively big reason actually is that garbage collectors don't tend to free memory in a more arbitrary order. They free less recently used objects. And so the new memory that we have to allocate that was recently freed is often has poorer locality, so it may have fallen out of the cache. All right, so any questions on these three high-level ideas so far? Oh, I don't have Slack open. Give me 1 second. Feel free if you want to shout out on Zoom too if you have any questions. But I will bring Slack up right now.
Yeah, there's nothing on Slack just now.
Cool. Apologies for me being behind. I have too many things to configure every time we set up. All right. So that was switch to lecture. So that was a really quick overview of our three main storage allocation ideas for today. So now we're going to spend the rest of today diving into each of them in more detail. And we're going to start out with stacks. So all you really need to implement a stack is an array of memory and a pointer, which we often call a stack pointer. That's the entire data structure. So at any given point in time, the allocated or used memory is everything between the start of the array and the stack pointer, which we're denoting by SP here. And everything after that to the end of the array is currently free unused memory. All right, so now what happens when we want to allocate a new object? So let's say we want to allocate X bytes of memory. All we need to do is this. And this is just sort of pseudocode written basically in C, but it gets at the basic idea of the core algorithms. So we first increment the stack pointer to make space. So that marks the next X bytes as being used. Quick aside, at this point, if we want to be safe, we should probably check and make sure we haven't allocated off the end of our stack array, because that would be what we call a stack overflow, which can cause memory corruption or memory errors. In C, the compiler usually doesn't generate code to check for overflow. Instead, for reasons we'll see with how memory and processes is laid out later, memory past the end of the stack is unallocated by the virtual memory system. So if you try to read or write past the end of the stack, you'll get a seg fault because you're trying to read or write past into uninitialized memory, and your OS's memory protection will catch it. So if that ever happens, you have to go fix your program. And you can either avoid allocating so much on the stack by having smaller local allocations in your functions and not recursing as deeply, or you can increase the stack size by recompiling your program and requesting a larger stack size, which you can do in a couple different ways. All right, so that was how we allocated X bytes of new memory by advancing the stack pointer. And now to actually get a pointer to that new memory, we return SP minus X. This return value is going to be a pointer to the start of the newly allocated object. So note that in some sense, it's a little weird to have to subtract from the head to get a pointer to that topmost object. So you can actually organize this a little bit differently so that the stack grows downward instead of upward, which many real systems and implementations do, I think, including most C implementations on x86. So then you'd start the stack pointer at the end of the array and allocate X bytes by subtracting X. And then the stack pointer always points to the start of the topmost object instead of its end. But this kind of integer math is basically free on modern processors. Compilers can be pretty good at optimizing it away, so it doesn't really matter that much either way. Okay, so that was allocation with a stack. Now, the next obvious question is how can we deallocate or free those X bytes? Not too surprisingly, we just subtract X bytes from the stack pointer. So that's going to move the stack pointer back, and the memory that was on the top is now considered free and can be reused. So it behaves just like we expect of a stack. So it's going last in, first out. The thing we allocated most recently is also the first thing to be freed. So now again, if we want to be safe, we should check for underflow, just like we needed to check for overflow on allocation. Okay, so that's everything you need to implement a stack allocator. It's really simple and efficient. Allocating and freeing takes order 1 time, but obviously it has this key constraint that you can only free from the top of the stack. So you can only allocate and free according to this simple stack discipline. That means it's only applicable sometimes. There's general programs which aren't going to fit this model. But when it works, it can be a great fit. When it's a fit, it's a really powerful and efficient technique. One question just came in: how large is the stack? So this depends on the default. It's chosen by a given C implementation. So in C and C++, the stack size is a parameter of the implementation. And with most C compilers, you can choose to customize it. You can choose to request a specific stack size. So I think a common setting on Linux and Linux on x86 is on the order of like a megabyte. Windows has a surprisingly small default stack allocation, which I've run into sometimes. Finally, a side point, you can explicitly dynamically allocate on the call stack as a user of C code using the alloca function, which you might recognize also as the instruction in LLVM that allocates stack memory. But this function is deprecated, and it tends to get in the way of the compiler doing its best optimizations, which it's able to do when it knows that the stack frames are fixed size, are like compile time constant sizes. So you can do that if you want to dynamically allocate a certain amount of extra space on the stack, but it's often a better idea not to. Okay, so we know we need something more general than just stacks to be able to manage memory. So now let's talk a bit about heap allocation. And let's start out with heap allocation for fixed sized objects or memory blocks. So this is simpler than the general case. We're only going to be dealing with allocating chunks of a constant size, a single constant size. But as we'll see in a bit, it's also a core subroutine that we can use to build more general arbitrary sized heap allocation. All right, so the first idea we could try to manage fixed size allocations is a simple bitmap. So the idea here is just use a bitmap to keep track of which blocks of our memory array A are free and which are used. So in this case, say this is the contents, like the status of all the blocks in our memory array, and this would be a corresponding bitmap. We could also take the complement of this bitmap. Here we're using 0 to represent used and 1 to represent free. You could also use the complement of that so that 1 would represent used and 0 would represent free, same difference. So we're using a bitmap here where we have 1 bit for each block in our array, storing the status, the free or used status of that block. So this works with block sizes that are arbitrarily small. And if you remember back to our Bitrix lecture, you might imagine that there's a bunch of clever low-level bit trick algorithms we can use to speed up the search for free blocks and things like that. But this is useful up to some scale. And schemes like this actually often are used in like disk and flash storage systems sometimes, for example, at some levels, or in parts of virtual memory page tracking. But in general, this approach is fundamentally not scalable to very large numbers of blocks. And that's because no matter how clever our bit tricks, those are just some constant time advantages. We still have to do basically a linear time search to find free blocks. All right. So bitmask is a simple scheme, but probably not what we want to use because of its linear cost of doing lookups. So a more scalable scheme, which we're going to choose to focus on instead, and what's closer to what you'd find inside a real like malloc implementation, is the idea of a free list. And the idea with a free list is that we'll keep track of unused memory blocks in a linked list. So we'll just have a list of pointers to blocks, each one pointing to the next free block in some order. And then a key trick that we can exploit is that we can store that free list in the unused blocks themselves. So if we assume that each piece of storage is at least as big as a pointer, like each block here is at least, say, 64 bits on our x86 64 machines, then we can use the first 64 bits of each block to store the free list pointers. So at the start of each unused block, we'll store a pointer to the start of the next unused block. Then the head of that list, this pointer free, is just a pointer to the first unused block. So in the state we see here on the slide, free points to this block here. Then the next pointer of this block points over to this block. Its next pointer points to this block, which points here, which is null at the end of the list. All right. See a question maybe coming in. Good question. So how do you know the data in the block isn't just random data instead of a pointer? So we'll see how we free things and put them back in the list, but it's going to be up to basically the implementation of free to make sure it sticks the right pointer in there. And when we first allocate this memory, we're going to have to take a pass over to initialize it. And we probably would do some pass that just makes a linear list with each item pointing to the next one or something like that. Okay. So now when we want to allocate one new object, we can just do this. So we can take the pointer to the head of the free list as the new object, change the head of the list to point to the next free block, and then return the new object. So let's walk through that in a little more detail. So first, we are taking the free pointer, storing that in X, which is going to be the object that we return. When we do that, like I keep saying, this code doesn't include checks, so we should probably check that we're not going off the end of the list. But that's an edge case that we'll talk a little bit more about later. Next, we advanced the pointer for the free list head, that's this free pointer, to point to the next free block. So we're doing this line of code, and that moves it over here. But assuming we haven't, oops, sorry. Right, yeah, so we just moved the free pointer to the next free block. Now we just return the pointer to the new object X. Okay, so that's the basic idea. Now, does anybody notice any issues with this? And feel free to shout out if you, or write on Slack. So ignoring the checking to make sure we aren't going off the end of the list, which I already mentioned. Does anybody notice any other issues with this? It's actually kind of related to some stuff that people brought up a second ago. No size check of X. You can't allocate more than a single block. Yeah, people are worried about allocating larger blocks. So Here, our goal is just, that's something we're going to resolve later with a layer on top of this. Here, our goal is just allocating things of fixed size of these contiguous blocks. So we have our whole job is to allocate fixed size blocks. Assume that's all we want to do, but there's still a potential issue with this. Somebody's thinking something about cycles. All right, so the thing I want to point out here is that we're potentially handing back a garbage pointer to the user code. So if we don't reinitialize this memory and we just hand it back to the user, we're giving a pointer directly into our free list data structure back to the user code. So different implementations can choose either to zero it out or to leave it to the programmer to decide what to do. It's implementation dependent. But commonly, programmers are going to want zero initialized memory. It's less likely to introduce weird bugs, and often zero initialization is a good starting state for data structures. So many implementations these days will zero initialize the memory also before handing it back. Okay, so once we've returned that memory to the user, this is our new state. So the block we returned is now used, and we have 3 unused blocks left. So any questions so far? I think some of the stuff is related to earlier discussion. We're going to talk about how you free them in just a second. All right. So that was allocation. Now the other obvious question is, how do we deallocate or free the memory in this free list scheme? Well, we just do the opposite. So if we want to free an object X, we would just reinterpret X as a free list item, set its next pointer to the current head of the free list, and then make X the new head of the free list. So in a little more detail, let's say X is this block here. So first, we reinterpret X as a free list item and set its next pointer to the current head. So now the start of X is a pointer pointing over here, which was a previous head of the free list. And next, we just move the free head pointer to point to the newly free block X. So it moves over here. All right, and now X is free, and this is the state of our memory and our data structure. So one thing to note about this scheme is that it acts kind of like a stack, in that the last thing that you freed is going to be the first thing that gets allocated. You see that? So because the last freed things always get pushed to the head of the free list, they'll be the first to come back when we allocate again. I wonder if anybody has any thoughts on why this might be a good property to have, particularly from a performance perspective. Absolutely, everybody's nailing it. Locality. The blocks that we just freed are likely to be in the cache when we allocate again. So data is probably like the blocks that we get back the next time we allocate are probably just sitting in L1 and are very efficient to touch. So it behaves like a stack by reusing the most recently freed memory, but of course, unlike a stack, you can still free the blocks in any order instead of just the last allocated one. So that's the key added generality, and the thing that leads to pointers kind of pointing all over the place instead of just pushing and popping on the end, like with the stack. All right, so that's how we can manage fixed size allocations with a free list. So again, allocating and freeing just take order 1 time. We saw we get a good temporal locality, which can lead to good cache behavior in some respect, because the things that we're going to return the next time we call malloc are going to be the things that we just freed most recently before. On the flip side, though, we get poorer spatial locality than with something like a stack. And that's due to what we call external fragmentation, which is wasted space in between the blocks. So notice that the free blocks are kind of scattered all over the place. So the blocks are distributed across our virtual memory space. The more kind of salt and pepper interleaving of free and used blocks we have, the less compactly stored the used blocks are. The larger the page table we need to store a given amount of used memory, the less efficient our TLB will be, because to touch the same number of objects, we need to traverse more virtual memory pages, the more sparse and spread out they are, and so on. So any questions on this so far? We just went through the basic algorithms for managing a free list for fixed size allocations. Any of that confusing? Maybe one question coming in. What's a TLB? Yeah, so this is just a side on an architectural detail that has some performance implications. So good question. The translation look-aside buffer, or TLB, is a piece of hardware acceleration for implementing virtual memory address translation. So you might have seen this in 004 or another architecture class. But basically, if you remember, our machines these days are outside of embedded systems. All the machines that you're writing code for use virtual memory. So your programs work with addresses that don't directly correspond to addresses in like cells of your physical DRAM. Instead, they have to go through a translation scheme to map to a physical memory address. And that's generally done at the granularity of pages, like 4 kilobyte pages commonly in most systems still. If you think about a load or store instruction that's going to take a virtual address as an argument, the hardware needs to be able to very quickly translate that to a physical address. And the translation look-aside buffer is a cache of basically pre-translated virtual to physical page mapping information that can accelerate that process for pages that have recently been accessed. But the problem is it's of a limited size, like any cache. And so if you reference many, many pages at once, some of them are going to fall out of the TLB, and you'll need to redo the whole virtual memory translation process when you try to access them. All right. So the key issue here was external fragmentation, the fact that we're scattering around the unused blocks all over memory. And we can mitigate this external fragmentation a bit by adding an extra level of hierarchy to our memory management in a sense. So here the idea is, instead of keeping a single free list, we keep a separate free list, or equivalently a separate bitmap for each of potentially many pages. So perhaps sized to match the pages of our underlying storage or virtual memory. We're going to have a set of multiple free lists instead of just one. And then instead of just allocating from anywhere, we always allocate from the fullest unfull page. And the idea here is that we want to bias the system towards packing fewer pages as full as possible to improve spatial locality by packing the used blocks closer together, which reduces the effect of this external fragmentation. So if you imagine we have, say, 2 pages of 10 blocks each, so 20 blocks in total, but only 10 of them are allocated and 10 are free, we can think of 2 different cases. So in this one, 9 out of the 10 are in one page and 1 is in the other. In the other one, 5 are in each of the 2 pages. So if you think about what happens in expectation for each case, we just imagine 2 random accesses to objects out of this set of 10. In this case, where 90% of them are in one page, the probability that those 2 random accesses both hit the same page is the probability of them both hitting the first page plus the probability of them both hitting the second page. So that's a combined probability of 0.82 in this case. So it's very likely that 2 random accesses are going to hit the same page. Whereas if things are more evenly distributed, the probability is only half. So we're better able to exploit locality when we pack things together more tightly in this way. All right. So that was how we can do a general heap allocation in the simplified case where all of our objects or memory blocks are a single fixed size. So now the reason fixed size free list allocators are important is that they're the core subroutine that we're going to use to build a general variable sized heap allocator, which is what I want to do now. So in variable sized allocation, the idea is to have free lists managing pools of memory for each of, in this case, R different size bins. So in each size bin, we only allow fixed size allocations. So our basic free list algorithm just works directly like we saw before. So each of these bins is just going to be a free list, a separate free list, like the free lists we saw before. All the allocations in that free list are the same size, but the different bins store successively larger sizes. We have different bins for different sized objects. So for example, a common thing you might do, we could have bins distributed by power of 2 sizes. So then bin K holds memory blocks of size 2 to the K or 2 to the K times some base constant. That gives us a logarithmic number of fixed size lists. Some people alternatively do Fibonacci number sequence for the size of the bins or other schemes, but the basic idea is the same. And a key idea here is that we're going to accept a bounded amount of internal fragmentation because we only have a limited number of block sizes, and each object won't necessarily fill up an entire block exactly. So internal fragmentation is in contrast to the external fragmentation we talked about a second ago. So external fragmentation was fragmentation of the free space in between allocated blocks. Internal fragmentation is when an allocated block is bigger than the size of the allocation we actually requested. And we'll see what that means and how that works in a second. But in general, what we get, we do get a limited amount of internal fragmentation in this case. It provides a nice trade-off since memory management is still almost as simple and efficient. It's literally just a constant factor more than with the fixed size free list. We basically just have a simple layer on top of our fixed size free list. So now when we want to allocate a block of X bytes, we just do this. So say we get, now an allocation isn't just a blind request for a block of the fixed size. Now we're able to request a specific number of bytes again. So first, given our request is for X bytes. So first we find the appropriate bin. In the case of power of 2 bins, that's going to be the ceiling of the log base 2 of X. So that's the bin containing the smallest blocks, which are at least X bytes. If the bin is non-empty, then we just, so if there's still free stuff in the free list of that bin, we just return the next block from its free list, exactly like we saw before. But otherwise, if the bin is empty, we have to find some free memory that we can use to allocate the block. So concretely, let's say that X is 3, so we want to allocate 3 bytes. So ceiling of log of 3 is 2. So we need to allocate blocks from bin 2, which if you think through our powers of 2, that's the bin that's supposed to store 4 byte blocks, which is the smallest size that can contain 3 bytes. But notice that bin 2 is currently empty. So what do we do now? So now we hit this this case here. So we're going to find, we're going to allocate memory for these currently empty bins by pulling it from the next highest non-empty bin. So what we do is look for the next larger bin that's not empty. That's in this case going to be bin 4. And then we take the next free block from bin 4, which is this whole big thing here. That's 16 bytes in this case with our power of 2 bins. That's a lot larger than we needed for X. But really what we're doing now is not directly returning a 16-byte allocation for this 3-byte request. We're instead breaking that apart to allocate blocks for the different smaller bins that were previously empty. So in this case, we get 2 blocks of size 4 bytes, correspond to what would have been in bin 2, and 1 block of 8 bytes for bin 3. So then we take one of the bin 2 blocks to return for the current allocation request, and stick the others into the corresponding free lists. So we bust this one up and put the pieces in the other free lists and return one of the ones of the size that we wanted. So now we have some free blocks in all of the bins and one more which we return for X. Okay. Finally, you should ask, what about if there are no larger blocks at any level? What if we read up to the top and everything's, all of the larger bins are empty? Well, in that case, we have to ask the OS to allocate more memory for our process first, and then we proceed through this process. So we'd have it, make some virtual memory allocation requests to give us some extra pages, and then we divvy them up among the bins and continue this way. Okay, any questions on this part so far? So great. So here notices that it seems like you could make adversarial allocation requests where you always request, in the case of these power of 2 size blocks, you always request 2 to the k plus 1 sizes. So in the worst case, the scheme only winds up about 50% full. And we'll get to an analysis of that in a second. That's a great observation. But I'm basically going to argue that that's not such a bad worst case. Quickly speaking of allocating memory from the OS, what I was saying we would do if we ran out of space in all of the larger bins, let's step back for a second and look at how virtual memory is laid out for C programs on most modern operating systems. So you might have seen this in an OS or architecture class, but really quickly it looks like this. So the address space of a process is broken up into segments arranged sequentially in virtual memory. So first, starting from the bottom, we have the text or code segment. Then we have a data segment, which is initialized from values stored in the binary on disk when the process is loaded. Then there's a special segment, kind of like the data segment, but for stuff that we know wants to be initialized to 0 when the program starts. So these don't need to actually be stored explicitly in the binary, so they don't take up space on disk, which makes storing the program more efficient and loading the program faster. Then we hit the heap segment. Then all the way at the other end of virtual memory, like I said, stacks often in most of the implementations you'll actually be using are often growing down. All the way at the other end of virtual address range, you'll often have the stack growing in the opposite direction. So when we need more pages to expand our heap for our heap allocator, we'll request new pages, growing off the end here, and the compiler will allocate whatever size is allowable for the stack at the other end, which tends to be, like I said, about 1 megabyte by default. It's a good question. What happens if the stack grows into the heap? So historically, this could be a problem. Usually you'd want some kind of protection to prevent that from happening, which you could implement different ways. You could have a guarded page in between the two that you're never allowed to allocate. And if the heap tries to grow into that, or the stack tries to grow into that, you'll get a seg fault. If the heap tries to grow into it, you'll get a seg fault. But remember that our machines today have 64-bit virtual addresses. So these aren't physical addresses in your 16 gigabytes of memory or whatever. These are virtual addresses in the space of 2 to the 64 addressable bytes, which is a really large number. So basically, we just know that that's never going to happen because the amount of physical memory we have and even the amount of backing storage we have on our storage system is many orders of magnitude smaller than the whole address space. So it's effectively impossible on modern machines to allocate that much. All right. So looking at that and thinking about just how big a 64-bit virtual address space is, one question you might ask is, why do we even need to worry about freeing memory at all? So if we just think about some of the fastest memory technologies today, so like GDDR6 memory on the latest latest NVIDIA GPUs, each chip, so each 32-bit channel can write about 64 gigabytes per second. Even the fastest GPU is only on the order of between half a terabyte and a terabyte per second that can write to memory across many different channels. So a 64-bit address space is going to take on the order of years to fill up. even if we're just streaming out at the maximum rate of our memory system. So from that perspective, we can effectively, never run out of virtual memory in most common systems that aren't going to be awake for that long. So why not just allocate into an ever expanding region in this huge virtual address space we have? Does anybody have any ideas? Why do we need to worry about freeing and reusing things? Locality? Yes, definitely. Any other ideas? Anything more fundamental or more catastrophic? Yeah, because memory has to be paged to disk if it's not freed. Exactly. So from the perspective that we've been talking about with allocators, basically the external fragmentation in this case would be horrendous. We would never reuse anything. We would always be expanding the range over which our used memory blocks are spread, and stuff that falls out of use is just going to become unused holes in the middle of that. And so the number of pages we need in our page table would expand arbitrarily. All of that, unless we know what's free and can be deleted, anything that gets paged out has to be swapped to disk, which is very expensive. Even our disk is probably not that big, many petabytes or whatever it is that corresponds to 2 to the 64. All right, so the goal of storage allocators here, from this perspective, is to try to let us use as little virtual memory as possible and try to keep the used portions relatively compact to minimize the internal and external fragmentation and get good locality and performance. All right, so now let's look really quickly at an analysis of the memory overhead of binned free lists. So let's suppose the maximum amount of heap memory in use at any time by our program is M. So I'm going to claim that if the heap is managed by this binned free list allocator that we just described, using power of 2 page bin sizes, block sizes, the amount of virtual memory consumed by the heap is upper bounded by M log M. And the basic idea here is that, as was pointed out by Mihir, an allocation request for a block size X is always going to consume 2 to the ceiling log X storage, which is at most 2X storage. So the worst case is going to be some large X that's equal to 2 to the K plus 1, some 2 to the K plus 1. We'll be using just shy of double the amount of storage we actually need. So the amount of virtual memory that's devoted to blocks of size 2 to the K is at most 2 times M. And then since there are at most log M free lists, this theorem trivially holds. So it's a basic intuition for the idea that the scheme is, in some relatively strong sense, not that bad. In fact, a bin free list turns out to be 6 competitive, meaning it's equivalent within a constant factor of 6, I believe, with a theoretically optimal allocator that is omniscient about all the allocations and frees that would ever happen. So it's even better than this bound, this simple to derive bound in practice. So relatively simple technique, but really quite powerful and effective. So one final trick we can apply to bin free lists is the idea of coalescing. And the idea of coalescing is, in addition to breaking apart large blocks to make new smaller blocks, we can also splice together adjacent blocks to reconstitute larger blocks. So there's different schemes people use for this that trade a little bit of overhead relative to the simple bin free list scheme. But it can help reduce fragmentation in practice. I'm not going to go into that in any more detail right now, so we can get ahead to garbage collection. All right, so that's it for heap allocation. And now I want to take a 2 or 3 minute breather break, and then we'll come back and talk about a couple of garbage collection schemes. All right. So to wrap up today, I wanted to talk a bit about different ways we can do garbage collection. And again, the idea is that we want to automate the process of freeing things so that we don't have to do it ourselves and introduce a wide class of bugs. And we're going to start out with a simple but useful scheme called reference counting. But first, what is a garbage collector in the first place? So the idea with garbage collection, again, is to free the programmer from having to free objects. So a garbage collector is some automatic system, mechanism, or procedure that can identify and free or recycle the objects that the program can no longer access. So garbage collection that you'll use most often is probably built into your language implementation and runtime in things like Python or Java. But it's also possible to implement these schemes yourself. And one of the simplest ways to do it, and the way you're most likely to encounter, is relatively common in modern C++ code, for example, if you've ever used smart pointers, is what's called reference counting. Now, before we get started with that, some key terminology for talking about garbage collection. So first is the idea of roots. So the roots of the GC are all the objects that are directly accessible by the program. So depending on the language or the semantics of the memory and allocation model you're working with, these are going to be things like global variables, variables allocated on the stack, etc. Then the live objects are the set of all objects that are reachable from the roots by following pointers. So those are all the things that it's possible for the program to see by dereferencing pointers that it has. And then dead objects are objects that are allocated but are inaccessible from the roots. So those are things the program has no way of seeing, and so they can be safely recycled. So then the question you might ask is, how can the garbage collector identify pointers? And different implementations work different ways. So in languages that have built-in garbage collection, it's common to do this via strong typing. So this is true of things like Java. So if the types of objects are all known at compile time, and you're not allowed to do things like pointer arithmetic, then the language and the language implementation knows how to identify everything that possibly is or could be used as a pointer to dereference memory by the program. Okay, so now let's look at our first garbage collection algorithm, and that's reference counting. So it's one of the simplest ways to do garbage collection, and the idea with reference counting is that we're just going to keep a count of the number of pointers that reference each object. And then we know that if that count drops to 0, that object is dead, it's unreachable, and so we can free it. So what you see here on the slide is a bunch of objects, and then we have 3 GC roots, which are maybe stack or global variables pointing into these other objects on the heap. The objects on the heap each are pointing to other objects, and each one carries with it an extra field, which is a reference count, which refers to the number of pointers pointing to that object. So you can see here, this has a reference count of 1, and indeed there's 1 incoming pointer. This has a reference count of 3, and indeed there's 3 incoming pointers. So let's quickly step through and see how this works. So starting out here, all these objects are reachable. They all have a non-zero reference count. So then let's change this pointer here and see what happens. So we change that pointer from pointing to this object to pointing to this object. We need to change the reference counts of both of those objects. The object that we used to point to, we need to decrement its reference count. And the new object that we're pointing to now, we need to increment its reference count. And those are the core operations that we have to do update a reference counting garbage collector state. So here we decrement the first one and get 0, and increment the second one and get 3. So now, remember the rule was that when the reference count drops to 0, this object is dead and we should free it. So now when we free this, we're going to notice some cascading effects because it has pointers elsewhere in the object graph. When we free this object, we remove its 2 pointers, and that leaves us with 2 more reference counts that we have to update. We have to decrement them because those pointers are going away. That stuff is no longer reachable along that path. We decrement those 2. Now we wind up with a reference count of 2 here and 0 here. And so over here now we have 2 objects that we freed and that we can recycle. So this is a nice and simple scheme, but there's a problem. Does anyone know what the problem is with reference counting? And it looks like we've foreshadowed it several minutes ago. So good job, Prem. Yes, exactly. So everybody's hitting on it. The key problem with reference counting is that there's no straightforward way in what I've described so far to deal with cycles. So according to the rules that the reference count keeps track of how many pointers are incident on an object, if we have a cycle of pointers, then there's no way that any of them are going to have their reference count fall to 0. They're always going to be at least 1 in the case of a simple cycle. And so they'll never be freed. So here, if we look at this slight modification of our object graph, we can see a cycle, for example, going through these objects along those pointers. That's the cycle there, highlighted in red. So because of that cycle, all these 4 objects over on this side of the graph have a reference count of 1, but they are not, in fact, reachable from the roots. If you look, the roots just hit these, just reach these 2 objects, and there's no pointers that get us into this other subgraph over here. So in fact, this is all garbage, but a simple reference counting scheme has no way of identifying that. And obviously, uncollected garbage stinks. So this is a limitation, a fundamental limitation of reference counting schemes. Some languages, like Objective-C, introduce extensions of this idea where you have both strong and weak pointers. So strong pointers increment and decrement the reference count, and weak pointers don't. And so if you want to build a cyclic data structure, you have to explicitly, thank you for cheering on the stale jokes. If you want to build a cyclic data structure, you have to make sure that at least one of the links in the cycle is maintained by a weak pointer. You'll see similar things in automatic management schemes using smart pointers in C++. But nevertheless, reference counting works really well for acyclic data structures, which are also quite common. It's efficient, it's easy to implement, like I said, even in at the user level in a language like C++. So it's a very powerful and useful technique that you'll wind up seeing in practice, even though it has some limitations. All right, so a more general strategy is mark and sweep garbage collection. So here, we're not going to keep track of the reference count anymore. Instead, we're going to mark everything that's reachable from the roots and then get rid of everything that we didn't mark that we therefore assume is not reachable. So the big idea of mark and sweep is basically that we're going to treat all the objects as a directed graph connected by their pointers. And then we're going to say the live objects are those that are reachable from the roots. We pass over the graph of pointers, marking all the objects, starting at the roots, marking all the objects that we can see. We can do, in this case, we're going to do a breadth first search, starting from the roots to find all the live objects. And then everything that we didn't mark is garbage and can be collected. All right, so let's see how this works. So we have a queue we're going to use to implement our breadth first search. And the queue starts out empty with a head and a tail pointer. And so the first thing that you do is you push the root onto the queue. And in this case, the root is this node R. So we push that onto the queue. And now you go through a loop where at every step through the loop, you're going to pop something off the queue. If it hasn't been visited yet, you're going to add it, you're going to traverse its pointers and add them to the end if they're not already in the list. So here, we're starting with the root. So we pop off R, and then we visit everything adjacent to R. So looking at the pointers out of R, that's going to be B and C. So we add B and C to our queue. Then we pop off B and check out all of its pointers. In this case, B only points to C, which is already in our marked list, so we don't have to do anything. Quick note, you'll notice we probably want some kind of auxiliary structure that makes it constant time to look up what pointers we've already marked rather than just having the queue, because we don't want to have to do a linear scan through this every time we're checking whether we should add a pointer, but that's sort of an advanced move that we assume is layered on top. Okay, so popping off B, we don't need to add anything else. We've already seen it all. Popping off C, we see two new pointers to E and D. We add those to our queue. Pop off D, doesn't add anything. Pop off E, gives us a new pointer to F. We visit F, gives us a new pointer to G. We visit G, and there's nothing new to be added. Now we're done. So now we've marked everything that's reachable from that root. And now we can just go through all the allocated pieces of memory and look to see, which things did we mark and which did we not mark. So that's the basic idea of mark and sweep. So in the mark stage, we do some kind of traversal. In this case, we're doing a breadth first search of all the live objects that are reachable from the roots. We keep track of them or mark them. And then in the sweep stage, we scan over memory to free all of the unmarked objects. We look at all of the allocations that exist to find any that aren't in our marked list and free those. Now you don't have to do breadth first search. You could do this in a depth first order or something else if you wanted. Breadth first just turns out to work well for a scheme we're going to layer on top of this in a second. But there is an issue with mark and sweep, and that's that it doesn't really deal with fragmentation. So we're just going to be, freeing stuff wherever it is, and just leaving objects spaghettied all over memory. So that's going to bring us to the last algorithm that I want to talk about, which is we can build on top of this breadth first mark and sweep scheme, and that's what we call stop and copy garbage collection. And again, here our goal is to solve potential fragmentation problems. So if you remember in our mark and sweep pass, this is where we were at the end of the sweep phase. But if you look now, all the live vertices, so if you imagine this stuff was allocated in some unknown order, and these various now garbage nodes that we should be freeing may be scattered in random locations. And that's where our fragmentation is going to come from. But if you look at the order what we've done with our queue, we've effectively built a densely packed list of all of the live vertices and placed it in some sense into contiguous storage in the queue. And that's the key thing. So this queue could just be pointers for tracking these objects, but that basic idea, that basic structural observation is what we're going to leverage to build a copying garbage collector. So in a copying garbage collector, we're now going to say we have two spaces of memory, a from space that we're collecting from, and then a to space that we're collecting into. So we're going to migrate and compact all of the still live objects whenever we do a collection. and that's going to help us eliminate fragmentation. So at any given point, we have our free list. It's going to have some mixture of live and dead objects and some free, potentially some free unused memory blocks. Then, we're going to go along, run our program, allocate something else, maybe free something, allocate some more stuff, free some more stuff, allocate again. And now at some point, the space in which we're working is going to be full. And this is the point at which we need to run our garbage collection. So now, the idea with the copying garbage collector is that now what I'm going to do is run the breadth first search of our mark and sweep collector. So we're going to do that marking pass. But I'm going to keep my breadth first search queue directly in the to space. So now whenever I visit an object in the from space, while going through the breadth first traversal from the roots, I'm going to track it in my queue by literally copying it into the next location than to space. Does that make some sense? So as we were traversing the pointers of these live objects, each time we add a new live object, we're literally copying it into our new destination memory space, but in this nice compact order that we get from the queue. All right. But there's one important detail here which I've ignored. And does anybody have any idea what that might be? Your guess is coming in? Yeah, great thought. Updating pointers. I just said we're copying objects. We know those objects have pointers in them, and presumably those pointers are pointing to other things in the from space. So we copy them over here. Now we have pointers to the older versions that we're trying to collect. Broken hearts. So the observation is that the address an object had in the from region of memory is probably not going to be equal to the address the object has in the to region of memory. We're copying it and moving it somewhere else. So the pointers have to be updated. And the scheme we're going to use is that whenever an object is copied to the to space, we're going to store a forwarding pointer in the from object that's implicitly marking that it's been moved and where it's been moved to. That's why we're going to keep track of what we've already moved. And then when an object is removed from the FIFO queue in the to space, so when we're popping it off the head, we're going to update all of its pointers. Or all of the pointers. Yeah, sorry, update all of its pointers. All right, so here's an example. So let's say we're in this state in the middle of a collection. So here's our from space with a couple of live objects. Here's our to and a bunch of dead space. Here's our to space into which we've been copying things. In each of our allocated objects in the from space that we've already migrated, we put pointers to the corresponding places where we've copied them into the to space. And then now where we are in our queue, these are the current contents of the queue. So this is the next object that we're going to be popping off from the queue. So we remove that item from the queue. We queue its adjacent vertices. So in this case, this has already been visited. So we're traversing its pointers for anything that hasn't been visited yet. This has already been visited, so we can leave it alone for the moment. This object has not been visited yet, so we need to stick that at the end of our queue. So we're going to copy it over to queue it and advance the tail. So this is a copy of what was there. The copy of this pointer still points to this object, just as the source version of that did. Then we're going to place those forwarding pointers in the from vertices. So we're going to stick a forwarding pointer from here to its new location. And then finally, we're going to update the pointers to the removed item to refer to its adjacent items in the to space. So the thing that we just removed, we have these two outgoing pointers in that object. So the last update we do to finish processing that object, to finish migrating it to the to space, is update its pointers by following these migration references. So this pointer is going to change to point to the new location of that object, and this pointer is going to change to point to the new location of that object. All right. So a question from Ayush. I thought these pointers were only present in the free space. Great question. So I think, yeah, the way we're drawing this, I think we're assuming in this scheme that often a garbage collector will have some augmentation, some additional fields associated with every object that's not part of what the user directly sees in that object. In the case of reference counting, that would be the reference count. In this case, I think we're assuming that we have extra space for these migration pointers in every object. So we have one extra pointer field that's maybe like right above or right after the object that we give to the user that we can use during this process. All right. So great. So that's the basic scheme for how we build a copying collector. Once we're done, once we've advanced the head pointer all the way over to here, we will have updated all the pointers in these objects to point into this to region of memory, and we can completely throw away what was in from. We're probably just going to then swap the to and from pointers. So the next time we do a collection, we copy from this region back to this other region. So this has some nice properties. It just takes linear time to copy and update all the vertices. At the end, we wind up with this nicely compacted layout of memory that doesn't have all the external fragmentation problems we've seen with many of the other schemes. So this is an advantage potential advantage of automatic garbage collection schemes, because if we're able to build a garbage collector like this, if our language is safe and abstract enough that we can implement something like this under the covers, then it's possible to change the layout of everything in memory and update all of these pointers so that we can basically defragment memory while we collect. So I mentioned some ways earlier on where garbage collection can potentially introduce performance overheads relative to explicit heap memory management. This is a way in which garbage collection can potentially give performance advantages. So it's not always a trivial trade-off. But there are a few issues with this still. So notice that we always need at least twice as much or more than twice as much space as our program is actually using, because we need a from space and a to space that have to be big enough to store at least all of the currently allocated objects. When the from space is full, we can basically, when we've used more than half of all of our memory, we wind up needing to ask the OS to give us more. Some nice characteristics of this: the cost of garbage collection amortizes to constant time, assuming that a user is generally actually working, like doing operations on all the memory that they allocate. And the space required is order 1 times optimal. Like I said, it's often something like 2x or a bit more than 2x in practice. Another observation with all of these schemes, but especially in this case where we're compacting things by copying, we make it a lot easier to release memory back to the OS when half of it's empty. So we can shrink the size of our virtual memory allocation for our process much more easily by defragmenting everything and then recognizing that we're only using a small fraction of the space, so we can give a bunch of it back to the OS. All right. So that's basically it for once I'm not running way over time. That's basically it for dynamic storage allocation. There's there's a very rich literature in this space. So we've just touched on some very basic ideas. It's worth pointing out that there's entire major conferences just dedicated to memory management schemes that have been running for decades. So there's literally tens of thousands of papers on these sorts of topics. Faster ways of building garbage collection, faster ways of building memory allocators of different kinds. There's all kinds of different strategies and optimizations and techniques that are helpful in different settings. So there's different variants of mark and sweep. We talked about coalescing schemes for reducing fragmentation in heaps. Garbage collectors, other important ideas in garbage collection are what's called generational garbage collection. So the idea there is that you don't always scan everything to potentially free. You keep your objects, you partition your memory into tiers of different age. So you're always allocating out of the newest tier, the newest generation. And then if objects survive past collection of that, the first collection in that generation, you promote them to the next generation. And the general idea is you run lots of collections on the young generations because objects that are going to be freed tend to be freed relatively quickly. And objects that are going to be long-lived tend to be quite long-lived. So you don't want to be constantly revisiting the long-lived objects only to find that, yes, they're still alive. And so you store them in, you heuristically exploit that by promoting them to higher and higher generations the longer they stay alive. And you only revisit the higher generations less frequently. There's different schemes for building real-time garbage collectors that have constant bounded overhead to work in real-time systems to limit pause times and such. There's multi-threaded and parallel schemes to be more efficient in modern multi-core systems, and on and on and on. And you might think even something like basic heap management for malloc is obviously a solved problem, but it turns out, there's a paper on, I'm forgetting the name, a researcher, Don Lejeune from Microsoft, has a new malloc engine that was published like a year ago that's dramatically better than anything anyone had before, that's now being used all across like Microsoft's internal systems and may take over the world soon. So even really basic stuff like the core of what we talked about today is still a frothy area of new ideas and new techniques. So it's a really, really fun and exciting area. Cool. So that's it for now, and I will let you go 30 seconds early, but I will hang out to chat with anybody who's interested. Thanks.